All right, in this tutorial we're going to build on our Gaussian resistor Monte Carlo setup and work toward doing a Monte Carlo simulation of the transfer characteristic of an R2R ladder DAC with Monte Carlo simulations. First, before we do that, we're going to actually do just a plain old resistive DAC with no Monte Carlo stuff, just to show you kind of how that works, because it's fairly involved to actually twiddle all the bits and get the transfer characteristic. So we're going to pull up a terminal window here, and we're going to cd documents DAC and we have here our Gaussian resistor symbol and Gaussian resistor definition symbol, and we'll do Xschem DAC and here you can see the circuit. I've made the circuit out of these Gaussian resistors, and the unit resistor here is a 10K, and the 2X resistor is a 20K. I've got my output current coming in or coming out over here through this last rung on the right. I've also defined or labeled this particular node V out. So in the resistive DAC, obviously the current flowing through this resistor times the resistance gives me a proportional voltage here, which I could also take as the output of this circuit. My input current sources are here dependent current sources. These are behavioral current sources, and the current is given by a parameter called Iref, which I've defined inside my Spice block to be 100 microamps, which is commensurate with a 10K resistor value, times the voltage on node B0. And so down here I have regular voltage sources, and they're between net nodes named B0 and ground, and the values here are just going to be 0 or 1 volt. Okay, so I'm just choosing that for convenience. And then I have six more of these here named B1, B2, B3. The voltage sources are named VB1, VB2, VB3, but the net names here are B0, B1, B2, B3, and so on. So that's it for the circuit. My Gaussian resistor definition block has the Monte Carlo switch parameter set to 0, so we shouldn't get any Gaussian variation. And then I'm going to go through the Spice block. Now I've put this in a code symbol instead of a shown code symbol because it's actually kind of long. And that's in part because the Ngspice interactive interpreter language leaves some things to be desired. So I want to step through this, and hopefully it will be understandable, although fairly clunky. So here's my definition of the IRF parameter at 100 microamps, and here's my control block. So the first thing I do is I set the built-in variable VRVec names so that we get the headings with the vector names in the first row of our output file. And we're going to set the WR single scale built-in variable so that we only get the scale, which is the thing that's nominally being swept by our simulation, only once at the very left-hand column of the output file, rather than once per vector we write out. So we're going to define a numeric variable here called code, which is going to be our DAC code word, and we're going to step through all of the 2 to the 7th possible code words, 0 to 127. So while code is less than 128, what we're going to do is basically extract the bits of this number, this code value. Now, unfortunately, this turned out to be a fair bit more complicated than I expected it to be, again, due to the limitations of the Ngspice interactive interpreter language, if you can call it that. So I was going to use the modulo operator. If you do something modulo 2, that basically tells you whether it's odd or even, and that would allow you to pick out the least significant bit of a number. And I was going to use division by powers of 2 to successive powers of 2 to shift the number over to the right by some number of bits. And I was going to use the floor function to basically truncate the fractional part, because these are floating point numbers. Unfortunately, the modulo operator in Ngspice doesn't know what to do with the number 0. That's apparently, you can't take the 0 mod something. It doesn't know that. And so I basically have to guard this in an if statement. So you have to test to see whether this thing that you're going to be taking the mod 2 of is equal to 0 or not, and treat that as a special case. So here we're saying if code is equal to 0, then B0 is 0. Otherwise, B0 is code mod 2. And then we're going to extract the first bit by looking at the floor of code divided by 2 and seeing if that's equal to 0. If it is equal to 0, then B1 is equal to 0. Otherwise, B1 is equal to the floor of code divided by 2 modulo 2. And so on down to the 6th bit, where we divide by 64. And so that is that. I also learned that apparently in an if statement you can't use the equal equals version of the equality test operator. You actually have to use the alias EQ for reasons which I'm not entirely sure of, but there you have it. And then what we're doing down here is we're altering the values of the various voltage sources according to the bits we've extracted from the code word that we're working on. And we're going to do an operating point analysis. So we're not actually sweeping anything here. We're basically altering the values of all of the input voltages to the right combination of zeros or ones. And we just want to do a DC operating point analysis. And that basically just calculates a single state of the circuit, and we're going to just basically write out a single line in the text file. And so our R2R data command is going to write the results out from this operating point analysis into a file called DAC2.txt that lives in the same directory as the schematic. And I'm writing out the bit values just so we can see that they're actually changing the way we expect. And then I'm writing out the current, the output current, and then the output node voltage. So on the first time through the loop, for code word 0, we want to set append right, which is a built-in variable that lets us append future results to an already existing file rather than overwriting it. So if we want to append all the successive operating point analyses results, we want to set the append right variable to true. And then in order to not have it write out the vector names again on every other line, we want to set WR vec names to false. And then we're going to bump the code up by 1 and go around to the top of the loop and then quit, and that's the end of the control block. Okay, so that's a fairly lengthy bit of code, and I decided to hide it inside of a code symbol here instead of doing a shown code. So we're going to write the netlist out, and we're going to simulate, and that was all it took to simulate. So it simulated very, very quickly. So we're going to pull up a new terminal window and have a look at our output results. CD documents, DAC2. There's our DAC2.txt, so we can do less DAC2.txt. And the scale it chose was net 1, which I don't even know what net that is, but this is the voltage on net 1. We're going to kind of ignore this. But here are our bit values. So you can see the least significant bit is alternating between 0 and 1, just like you expect when you count in binary. The next bit up is alternating on every second count, so 0, 0, 1, 1, 0, 0, 1, 1. And then the third bit is, or the bit 2 is 0, 0, 0, 0, 1, 1, 1, 1. So it's alternating on every 4. B3 is alternating out every 8, then every 16, then every 32, then every 64. And then up at the end we get 1, 1, 1, 1, 1, 1, 1, which is what we want. And then these are the output currents, and this is the output voltage. Okay, so that's good. Now we're just going to import this into my little Python environment. And let's see, so we're going to load Ngspice DAC_toot.text. And there's our vector of bits, which we don't really care so much about. We're going to say maybe I out equals V I out, just so it's a little more sensible. And then we're going to create a code vector, which is going to be a NumPy array generated from a list from range 128. That will give us the code words from 0 to 127, so we can basically plot code, comma, I out. And there's our DAC transfer characteristic. It's nice and linear, like you might expect. It goes from about 0 microamps up to something like 130 some odd microamps at full scale. Can kind of zoom in here. And see that it's nice and linear with uniform steps, which you would expect if there's no mismatch and everything is ideal. So that's the DAC transfer characteristic with no variation. Okay, so we're going to now move on to doing Monte Carlo simulation with variation, building on this rather clunky way of twiddling the bits. But hey, it works. So let's Xschem MC DAC_toot.sch. And so this is the same circuit. The only difference is the control block. So I'm going to start out with the MC switch off, and we'll actually walk through the control block with the Monte Carlo loop around the code loop or code word loop, and then we'll simulate without the variation to see that we get all of the transfer curves on top of each other, and then we'll do the simulation with the transfer curve. Okay, so here I basically have the same setup for the innermost loop, but I've just moved it in by indenting it by 2 more spaces here. And I've put around it a second loop that is going to loop over the Monte Carlo runs. So I'm going to do 10 runs. Obviously I could do 100 or I could do 1,000. The results are just going to be written out in that many text files. And we're going to again embed the name, or we're going to embed in the name of the text file the Monte Carlo run number. So we're going to do 10 runs in this example. We're going to set the counter that we're going to use to loop over the runs to 1. We're going to say while run is less than or equal to runs. And now inside of this loop, we're going to set append right equal to false. So when we start a new Monte Carlo run, we're going to want to start a new text file to store the results in. And if there was a previously existing text file with that name, we're going to want to overwrite it. And so we're going to set append right to false. And then we're going to set WR vec names so that on the first line in the file we get, when we start a new file for a new run, we're going to want to turn the vec names writing on by setting this built-in variable to true. And then we're going to just embed that same loop that we had to extract the bits and step through all the code words as our inner loop here. And so we're going to set let code equal 0, and while code is less than 128, we're going to extract the bits from code. We're going to alter the VB voltage sources accordingly. We're going to do an operating point analysis. And now we're going to save the results of the operating point analysis into a file which is going to be called MC-DAC2, some run number embedded in here, .txt. And again, we're writing out the bits. Obviously, you wouldn't have to do that if you didn't want to. You could just put the output current here. I'm putting the output current and the output voltage. And again, if we're on the first time through the inner loop, we want to turn append write on so we can write successive lines for this Monte Carlo run to the same file. Obviously, on the inner loop, we're not going to be changing this number, so it's going to be all written out to the same text file until we bump the run value up by 1. And we're going to want to turn off writing a vector name so we don't get the vector names repeated on every other line. And we're going to bump the code word up by 1 and then go around the inner loop until we're done with that. Okay, so once we get done with one set of 128 code words, then we're going to issue the reset command. The reset command is going to generate for us a new set of pseudo-random resistors if we have the Monte Carlo switch turned on. And then we're going to bump the run number up by 1 and go around the outer loop again, and then we're going to quit. And that's all there is to it. And like I said, we're going to run this first with no Monte Carlo variation and see that we get 10 voltage 10 transfer characteristics. It's actually code word to output current transfer characteristic here. So we're going to netlist and then run the simulation. You can see it does take a bit more time because we're doing basically 10 times the number of simulations. Let's lower this one. So now we have our MC-DAC2 1 through 10, and we're going to go into my Python environment, and we're going to write iout. I'm going to make an empty list for iout. I'm going to basically append all of the successive output current vectors here to that vout. I'm not going to deal with the vout. So let's see, for I in range 1 to 11, load Ngspice format MC-DAC toot. I'm going to insert index in there .txt. And then we're going to do iout.append v-iout, and boom. Now we're going to generate the code the same way we did before. It's going to be array of list of range 128. And we can do plot code comma iout. And now we actually have 10 curves here, and they are all on top of each other. And so we're not going to be able to distinguish them, but we can look at iout, and we get basically 10 lists of numbers, and if we were to check these numbers, they're all identical to each other. So that's just what we wanted. So now let's exit this, and we can go back here and turn on the Monte Carlo switch. And we can save that. Re-netlist and re-simulate. And those all have modification dates that are consistent with them just having been generated, which is good. And let's go back into my Python environment and make I out, and then we'll loop through 1 to 11. And we're going to load Ngspice format string MC DAC toot, embed I in there, and then we're going to have iout.append v-iout. And our iout is a list of 10 NumPy arrays. We're going to generate our code array. We can do plot code iout. Now you can see there's some variation here in our code, or in our transfer characteristics. You can see they're sort of wandering around. If I zoom in here, you can kind of see that there are non-uniform steps and there is some spread, which is commensurate with having variation in the network. And so hopefully that will give you a template and some useful tools for simulating the transfer characteristics of your MOSFET R2R ladder like DAC. And I'll also include some Monte Carlo simulations in that. So that's it. Thank you for watching, and hope it's helpful.